Hello, this is Anatomy of the Periodic Table. This is part 2 of the lecture, part of the Elements and the Periodic Table chapter. If you remember at the beginning or at the end of part 1 of this lesson or lecture, we were talking about the 3 different types of elements on the periodic table. We already looked at metals. Now we need to look at nonmetals and metalloids. Real quickly, I use the analogy with the 3 different types of elements on the periodic table. Please don't get confused with phases of matter, solid, liquids, and gases. Theoretically, anything can be a solid, a liquid, or gas. You just have to put it under the right conditions. But these are the types of elements. So I kind of think of them as like the races in like a video game or something. You've got, I'm going to nerd out here for a second. You've got your orcs, and then you've got your elves, and then you've got your humans. So like the 3 different kinds of races. So think of them that way. Picking up with nonmetals, you'll see that they are the gold colored elements in this periodic table, and they're all on the right hand side except for this little duber right here. He's the couch hopper. Sometimes he belongs over there with group 1, and sometimes he belongs over there with with the noble gases, group 8, or maybe even group 8A or 7A. All right, so what makes a nonmetal a nonmetal? Well, most of our nonmetals are gases at room temperature. We do have a few solids, and if they are solid, they tend to be dull. That's their luster, as in not shiny, but dull. They tend to be brittle, which means that it's hard, like you can't squeeze it, but if you were to put force on it, it would break pretty easily. Brittle. They tend to be good insulators. Insulators are the opposite of conductors, which means they do not allow heat or electricity to pass through them. And finally, they tend to be found to the right of the metalloids on the periodic table. And like I said earlier, hydrogen is not found to the right of the metalloids. It's the one weirdo. It's way over there on the left-hand side. Here are some examples of nonmetals on the periodic table. This right here is chlorine. It's a gas. The only reason I showed you chlorine gas, I've shown it to you guys before, is just because you can see it. It's a colored gas. Most of our nonmetals are gases, like I said before. That's one of the properties. If they do tend to be solids, here is sulfur. Notice what am I showing you here, that it is dull in luster, and that it's also solid at room temperature. And then here's a picture of sulfur as well. What property of sulfur am I showing you? This is a note check. Come tell me what property of not sulfur but of nonmetals I'm showing you with that picture. The third and final type of element on the periodic table are metalloids. That's, of course, the fewest. They're the purple ones right there. Metalloids are kind of the transition between metals and nonmetals. They have properties of both metals, and sometimes they have properties of nonmetals. Our metalloids are boron, silicon, germanium, arsenic, antimony, and tellurium. Sometimes polonium and astatine are considered metalloids. It just depends on who you're talking to and which periodic table you're looking at. On the periodic table, you find the metalloids sitting on the actual dividing line, the line of demarcation between the metals and the nonmetals on the periodic table. A lot of periodic tables show this line as they bold it on the periodic table. It's a bolded line, or maybe a red line, a different colored line going through the periodic table. I will usually, if I talk about that line, I'm going to refer to it as a stair step. The only time I talk about it, of course, is if we're talking about the metalloids. I say, okay, look at the metalloids. They sit on the stair step all around it. Here's my example of a metalloid. That's boron. To me, it looks like a cornflake that would kill you. So let's look at why I chose this as my example for a metalloid. Okay, remember, metals are good conductors. Nonmetals are good insulators, the opposite of a conductor. Boron is an insulator, a good insulator at room temperature, but you heat that sucker up and it's suddenly a good conductor. So it has properties of both metals and nonmetals. Now we're going to look individually at each of the main groups or families on the periodic table. There are 8 of them. Before we jump into the groups really quickly, a quick note about the numbers on the periodic table. Most of the periodic tables that you run into nowadays, they're all grouped 1 through 18. That's not how I learned it, and I have trouble using 1 through 18. So some of the older periodic tables, if you find them, or if you're listening to me, you're going to hear me call the groups by different names sometimes, because I'm older, and the older way to number the groups involves letters and Roman numerals. So the letters are A and B with Roman numeral in front of them. The main groups are labeled with an A. The transition elements are labeled with a B. And usually it's just when I'm talking about the main groups that I use the strange strange to you groupings, but they mean they have more meaning to me. To me, it's easier if you learn them this way. So the main groups go from 1A to 8A. You skip the transition elements. If you think of the periodic table as looking like a canyon or a U-shape, that's not a good color, looking like a canyon or a U-shape, there's my little canyon. Your main groups are going to be right here. And so those are the walls of the canyon, and so if you're looking at it, you're going to skip this part. So it'd be 1, 2, 3, 4, 5, 6, 7, 8. See? All right, and then those are all A's. Here, if you need to, you can pause and look at this picture. It shows all of the numbering systems for the groups. So the only problem is that they messed up on group 1. They messed it up a little bit. So don't look at group 1. Look at the rest of the groups. But you can see they have the numbering system that you're used to, the 1, 2, 3, 4, 5, 6, all the way through 18. And then they have the Roman numerals with the letters. So all of these guys are group 1A, group 2A. You skip the transition metals. Group 3A, 4A, 5A, 6A, 7A, and 8A. And then if you don't like Roman numerals, they have it listed below with the actual numerals. So rather than group VA right there, they show group 5A. And let me remember to mention that the transition elements, remember I skipped them. Well, when you come back, they're numbered very strangely. I've never studied the transition elements and why they're numbered that way. I'm guessing it has something to do with the valence electrons, but they are the B elements. So 3B, 4B, 5B, 6B, 7B, 8B, and then you go back to 1 and 2B. So there you have it. Now let's jump into talking about the groups individually. We're going to start right here with group 1 to you, 1A to me. Those are called the alkali metals. They include, hold on just a second here, boom. They include lithium, sodium, potassium, rubidium, cesium, and francium. If you're reading a periodic table from Europe, they're going to spell cesium with an A, C-A-E, S-I-U-M. All right, so all of these guys here in group 1A or group 1 have one valence electron. Is it easier to go out and gain 7 electrons, or is it easier to just go ahead and get rid of 1 electron? The answer is it's easier to get rid of 1. So these guys very easily lose that 1 valence electron. Remember, if you lose an electron, it's backwards world, you're becoming positive, cation, so they form a 1 plus cation. These, because they lose that electron so very easily, these are the most reactive group of elements on the periodic table. That makes them also one of the most fun elements or groups to play with on the periodic table. Here's a picture of some of your alkali metals. You've got lithium, sodium, and potassium right there. Notice that lithium is floating in something. It's in probably a mineral oil right there because lithium is so reactive, and if you look at it on the periodic table, it's actually the least reactive of the alkali metals, but it's still so reactive that they have to keep it in mineral oil because if it gets into the air, it will oxidize extremely quickly and turn kind of that nasty color. It doesn't look like a metal anymore. It looks more like a white cheesy thing. And then also, if it touches any water, it'll essentially start smoking and eventually catch fire. Sodium, you put it in water and it will not oxidize. It will extremely quickly react and you can have a nice little explosion if you have a big enough chunk. And then the rest of them going down the the group, they get even more reactive with water. I believe potassium will just catch fire. So they're a lot of fun to play with. You can go look at videos on YouTube. As a matter of fact, come to me. I have some really good videos to show you about the alkali metals and people playing with them with water, because they're, like I said, they're so very, very reactive that they're a lot of fun to watch people play with. They're all metals. They're all solid at room temperature, they're all malleable, they're all ductile, and they are all good conductors. Remember, those are all properties of metals, and I've already mentioned how very reactive they are. Remember a couple of slides ago, I pointed out the alkali metals, and then I said, whoops, and I put a little X on hydrogen. Hydrogen's our exception here. Hydrogen is usually an exception if we're talking about the periodic table. Hydrogen is not considered an alkali metal. Why? Well, first of all, it's not a metal. And its properties are different from the rest of the alkali metals. Why is it there? Because it has one valence electron, just like all the rest of them. It just doesn't behave the same way. And we'll study more about that later. Now we have group 2. I call it group 2A. I just cannot call it group 2. So group 2A right there, those are the alkaline earth metals. Please be very careful. Alkali metals are the first group. Alkaline, don't forget that NE in there, earth metals are the second group. A lot of people get confused and will call group 1 alkaline or group 2 alkali earth metals. So be very, very careful how you do that. They include beryllium, magnesium, calcium, strontium, and radium. All of these guys have 2 valence electrons. Again, is it easier to go out and get 6 electrons? Remember, everybody wants 8, except for a few exceptions up here at the top. These guys up here at the top, they're the exceptions to the rule. But a few of them, most of them want 8 valence electrons in order to be fully stable. Is it easier to gain 6 electrons or to lose 2? If, all things being equal. It's much easier to lose 2 than to go out and find 6 more. So they do that. They tend to lose 2 valence electrons pretty easily, and so they form a 2+ cation. Again, cation is positive. If you're losing electrons, you're becoming positive. The charge comes from how many electrons did you lose. You lost 2, so you have a 2+ cation. These guys are still very, very reactive because losing an electron apparently is pretty darn easy, which makes you very, very reactive. But nobody is as reactive as the alkali metals in group 1A. Here are some examples of the alkaline earth metals. They are metals. All of them are metals. They're solid at room temperature. They have properties of metals. They're malleable, ductile, good conductors, and these guys are also highly reactive. You can tell how highly reactive they are because, you can see them being kept in water or mineral oil. It's hard to tell. Probably not water. And this one is being kept in, I think, probably an argon in case there's probably argon gas in there to keep it from oxidizing and crusting over. The reason I showed you this picture right here, and you can see it right here, is calcium surprises people. You hear about calcium from when you're a little kid. Drink your milk, you need calcium for your bones to be strong and all that. And we think of calcium as being kind of a white powder, mostly because if you take the vitamin, and we're always shown calcium to be a white powder. Well, calcium is a metal, and that surprises a lot of people. And that is what calcium really looks like in as elemental calcium. So, like I said, it surprises people. Magnesium is fun to play with. It catches fire in the air, I believe, sometimes. Now we're going to jump over to the right-hand side of the periodic table for the halogens. Halogens, I call it group 7A. You guys will call it group 17. There they are right there. They include fluorine, chlorine, bromine, iodine, and astatine. All of these guys have 7 valence electrons. So if you have 7 valence electrons and everybody feels stable with 8 valence electrons, is it easier for you to go out and gain 1 electron, or is it easier for you to lose your 7 valence electrons to feel stable? All things being equal, it's much easier to go ahead and gain 1 electron. Remember, a backwards world, if you're gaining an electron, you're becoming negative. So all of these guys form anions, negative ions. because it's just involving one electron, these guys are very reactive as well. The halogens are very reactive. And just a little note, this is the only group that has both or all three solids, liquids, and gases in it. So fluorine and chlorine right there are gases. Bromine is one of the two liquids on the periodic table, the other one being mercury. And then you have your solids right here. Who knows what an unseptium is? Here are some examples, some pictures of some halogens. Here is chlorine right there. And chlorine is a gas. There is bromine right there. Bromine is one of our two liquids at room temperature on the periodic table, the other one being mercury. And here is iodine right here, and iodine is a solid, so I'm just showing you that. Notice iodine is pretty in purple, bromine is not so pretty reddish brown color, and chlorine is a mucousy sort of sick yellow-green color. And remember, these guys are very reactive. Moving even further to the right on the periodic table, we have our final group on the periodic table, the noble gases, group 18 to you, group 8A to me. They include helium, neon, argon, krypton, xenon, and radon. We don't know about unknown octium right now. And all of these guys have a full outer shell, 8 valence electrons. Helium's a bit of an exception. It doesn't have 8 valence electrons. It has 2, but its outer shell is still full, so it is, in fact, a noble gas. Why are they called noble gases? Well, these guys are inert. If everybody is stable with 8 valence electrons, these guys have 8 valence electrons already, so they don't react with anybody. They don't need to in order to feel stable. They already feel stable. So they're noble because they don't go around interacting with anybody else, just like the nobility. They stick their noses up at everybody, and they think they are better than everybody. And are they? Probably. Here are some examples of noble gases. One of the fun things about noble gases is this is where you get all your quote-unquote neon signs. Not all of them. You've got some halogens in there as well. Halogens, by the way, if you're like, oh, halogen lights, yes, that's exactly where they come from. But we're not talking about those right now. We're talking about noble gases. If you remember in chemistry, we can always make chemistry more fun by setting things on fire. Well, you can also always make things more fun by throwing electricity through them. So we take our gases, our noble gases, you throw electricity through them, and they produce pretty lights. When we get into the light spectrum and everything, I'll explain to you how and why this happens. That's a fun lesson. But you can see the pretty colored lights that they create whenever you throw light through them, and this is how we get what we call neon signs. Neon is only ever this color when you put electricity through it. So I believe Celine did this in her presentation on neon, and she explained if you see a neon sign that has any color other than that one right there, it's not neon. It's a mixture of other gases, or if you see one of those colors specifically, it is that gas. All right, jumping back to the left a little bit, we're going to go through some families on the periodic table that aren't very often talked about, not at least by your book. Group 3A, or group 13 to you, is called the boron family. It includes boron, aluminum, gallium, indium, and thallium. All of these guys have 3 valence electrons. Boron is a metalloid. The rest of them are all metals. And everybody except for boron in there is a metal that is soft, so like you could cut it with a knife type of soft. I'm going to talk about all of these groups here in just a moment, and why I'm not explaining what kind of ions they form. Here are some examples of the boron family, and I'm showing you the examples because these are kind of fun examples. Notice, again, these are soft metals that you can cut with a knife. Your alkali metals also, you can do this. They're very soft like butter or cheese. You can cut them with a butter knife, essentially. Aluminum is fun. You guys can go get some foil and play with that. Gallium is the neat one. Gallium, mercury is the only metal at room temperature. Gallium has such a low melting point that if you set it on the on the table, just out in the room, it's a solid, just like, aluminum or indium right there. But it has such a low melting point that you put it in your hand and it'll melt. You don't want to do that. It's toxic. It's not so bad that it's going to kill this person who's holding it, but it does seep into your skin just like mercury does, and it's a neurotoxin just like mercury is. So you don't want to play with it on a daily basis. And you see, wear gloves if you ever find some gallium. Jumping over one family to the right, we've got the carbon family. This is group, what are we on? 4A or 14 for you guys. These guys are also called the tetragens. Why tetra? 4 tetras. Because they have 4 valence electrons. They are carbon, silicon, germanium, tin, lead, and flerovium. These guys, all of these groups right here, these 3 right here, they react a little bit differently than the main groups that we have been talking about previously, the halogens and all of those. And so because of that, I'm not going to really talk about whether they form cations or anions. It's a little more complicated than that. So that's why I'm not discussing that. But it is important to know that they do have 4 valence electrons, because that does affect how they react. And these are pretty varied. As far as the main group elements go, this is probably one of the more varied as far as their physical and chemical properties. But having 4 valence electrons, they all do still react similarly. A quick note on carbon really quickly, right there. Carbon is such an important element in chemistry. It's actually a really neat element to look at, because if you look at diamonds, if you look at coal, if you look at the graphite in your pencil, those are all carbon, and it's just a different configuration of how the atoms have set up in there. But carbon is such an important and interesting element in the world to us that it has an entire class. If you learn chemistry in college, you'd take an entire class on it called organic chemistry. But it's also an entire section of chemistry. There are people who dedicate their entire careers just to the study of carbon. So that's how important it is. Moving one more group to the right, we are now in group 5A, I believe now, or 15. This is the nitrogen family. Nitrogen, phosphorus, arsenic, antimony, bismuth. All of these guys have 5 valence electrons, and this group also has varied properties as well. You have solids and gases. And again, I'm not going to talk about them because they react a little bit differently, but it is important to know them. Group 6A, the oxygen family, also known as the chalcogens. I've always remembered that because it's just a fun word to say, chalcogens. Also, you say it differently than it looks. Oxygen, sulfur, selenium, tellurium, polonium, and livermorium. All of these guys have 6 valence electrons. They do form anions. If you have 6 valence electrons, you want 8. Is it easier to gain 2 electrons or to lose 6? All things being equal, it's easier to gain 2 electrons. If you've gained 2 electrons, you have become negative by 2. That means you are a 2- anion. We finished with the main group elements. Now we're going to look at the transition elements, including the inner transition elements. You'll see me write transition elements and sometimes write transition metals. I use those interchangeably. Is that correct? I have no idea. I grew up calling them transition metals. Your book calls them transition elements. I think technically both are correct because all of them are metals. So let me circle them. Your transition metals or elements are the floor of the canyon on the periodic table. So you've got all of these are metals. Most of them have high melting points. Very often, when they do form compounds, they form colored compounds. That's pretty cool. Some of them are radioactive. What does it mean to be radioactive? You hear this all the time. You know it's not good, probably. So what does that mean? It means that the nucleus of the atom, where the protons and the neutrons are, that's not stable. It tends to fall apart. Some of them very easily, some of them not very easily. The more easily you fall apart, the more radioactive you are and the more dangerous you are to human beings. This group they call the transition elements or the transition metals because they're not as easy to, it's not as easy to figure out how they're going to react as the others. And we'll look into that here in just a moment, a little more in depth. All right, now we're just looking at the transition metals by themselves. We're not looking at the inner transition metals right now, just the floor of the canyon right there, not the guys that got pulled out. All of these are metals. All of these tend to lose electrons. If you lose electrons, you're losing negative, so you're becoming more positive. That makes you a cation. Remember, the way you remember that is that cats have paws, and so cations are positive. Isn't that adorable? Okay. These are your transition elements because, unlike the representative elements, the transition elements, it's hard to predict how many valence electrons that they're going to lose. The representative elements are called representative elements because each one represents its group very, very well. Lithium, and potassium, they represent the alkali metals really well. And so they're kind of like the homies in the gang. They're like, I'll stand up for you. I represent like that. They're good. Whereas the transition metals, they're like, what, you need $10? I got 20, but I'm going to use it later. I can't help you out with that. They're harder to they don't represent as well, is what I'm trying to say there. One of the ways that makes them difficult to predict how they will react, or one of the reasons, is because that a lot of them can form more than one different type of ion. So iron, chromium, all of these, I think scandium, copper for sure, zinc, but nickel is the example I'm going to use. Sometimes it forms a 2+ ion, sometimes it forms a 3+ ion, and it depends on what's around, but that makes it hard to predict like how it's going to react with others, the fact that it can do that. Let's talk about the inner transition elements for a second. The inner transition elements are these doobers down here. And you may at this point be asking yourself, all right, myself, why are these things called inner transition elements when obviously they are outside the periodic table? They've been pulled out. Here, let me show you. I don't even have to explain it. I'm just going to show you, but on the next slide, what the periodic table actually should look like. Ta-da! Now you can see for yourself why those guys are pulled out and why they're called inner transition elements. Because when it comes time to use a periodic table, nobody's got room for that. As I said before, the inner transition metals are the two rows that are pulled out of the periodic table. Those are our inner transition metals. Now we're going to look more closely at each one of those two rows. The top row is the lanthanide series. We usually just refer to these elements as the lanthanides. Why? Because the first element right there is lanthanum. All right, so these guys actually belong in period 6 right here. I showed you the picture just the last slide, so you get it. You understand where they go. Lanthanides. There's not much to say about them. The bottom row down here, these are the actinides or the actinide series because you've got actinium right there. They belong on period 7 right there, and they are all radioactive, and most of them are man-made. That brings us to the end of this presentation. Get ready for the quiz and the test. The test is going to cover the last, 4 lectures, and the quiz will just be over the anatomy of the periodic table. And don't forget, you still have element quizzes that you're working on.